presenting on the relay feedback modeling for the red team. Other members of the red team are Chris Burns, Chris Jenkins, and Clay Hoover. And our station is the filter wash station with both valves open. Overview what we'll be talking about today is, first of all, we'll look at a brief system overview. Then look at the steady-state operating curve, followed by the relay feedback experiment. Then we'll look at the new stuff, which would be the relay modeling, theory, results, and conclusions. Here's the schematic of our filter wash station. The flow rate controller gets signal from the computer, which sends it to the actuator, which sends the signal to the pump, which pumps the water, and the flow rate transmitter records the flow rate and sends it back to the controller. For our case, both of these valves remain open, so the flow goes to all three stations here. This is the block diagram of our system. The input for our system is in motor power, which is a percentage, which goes to the filter wash pump system, and the output is wash water flow, which is in pounds per minute. This is our steady-state operating curve. We found the linear range to be from 50 to 100%, and we broke this down into three regions, 50 to 67, 67 to 84, and 84 to 100% to run future experiments on. The slope in the linear range is 0.1 pounds per minute per percent. For the relay feedback, the parameters this is the parameters I used. You have to use the entire range from 50 to 100% because when you use a smaller range, you can't see the response in the output. The set point comes from the middle of the operating range, which would be 75%, and you go up to the SSOC and over to find your output of that. 15 pounds per minute. The floor and ceiling is a quarter below and above the range, which would be 62.5 and 87.5. Then the controller gain is just a large number. Using those parameters, you get this graph from the relay feedback. The ceiling and floor are shown here for the input as it varies up and down, oscillating. The delta M is the distance between those two. Period is the time it takes for one cycle to repeat itself. And then delta C here is the height of the output as it oscillates up and down. Speed is for the relay modeling, and it is half the output at half the height above the set point line here, and then the time it takes to go from there to the peak of the output. I ran another experiment to compare data to, and I just used the same parameters except left the ceiling and floor at 150%. So it looks similar, but the input and output oscillate at a higher height. To get the ultimate frequency and ultimate gain from the relay feedback, we use these two equations here. Ultimate frequency is 1 over the period, and the ultimate gain is 4 times the delta M over pi delta C. Using these, this compares the ultimate frequency and ultimate gain for each of the two trials. And you can see the numbers match pretty well, but the uncertainty and the gain here is a little larger than the frequency. Then averaging these values together, you can compare it to the Bode plot, which got 0.40 plus or minus 0.02 from the relay feedback, which compared to our Bode plot answer was 0.60 plus or minus 0.19, which is within uncertainty. And the ultimate gain from the relay feedback was 24, as well as the Bode plot was 24. So those match pretty well. So relay feedback matches with the ultimate frequency and ultimate gain from the Bode plot. To get the FOPDT parameters, these formulas can be used in the relay modeling. The FOPDT parameters that I found are tau, dead time, and K. But to get to these, a lot of other calculations had to be done. First, you have to find the curvature factor, which is 4b over that period, and then the omega is 2 pi over the period. And then, since there's two unknowns in this equation down here, you have to find a ratio from the dead time to tau, which uses this equation here, where f is the curvature factor. And then 10 to the above answer knocks out log and 10, and you're left with this ratio, which we just call c. And with all this known, you can find your tau in this equation here. And then with that known, you can go back to this c and find your dead time, and k equals the square root of 1 plus omega tau squared over kc. So using that and both of those trials, here's the data I got from both of those. The tau and k seem to be about the same answer in both trials, but the dead time varies a slight bit, but not too bad. The only problem here is the uncertainty, and this time constant seems to be a lot larger than the other ones. Then averaging those values together, you get, for our dead time from the relay modeling is 0.64 plus or minus 0.02, and our time constant is 1.9 plus or minus 0.68, and k is 0.23 plus or minus 0.08, which compared to the Bodie plot, the tau dead time here is about the same number, not too big of a variation here, but the tau and k are about double what you get from the Bodie plot, which doesn't really agree with the Bodie plot FOPDT parameters. So in closing, relay feedback agrees with the ultimate gain and ultimate frequency you get from the Bodie plot, but from the relay modeling, you get the FOPDT parameters, which doesn't tend to agree that well with the FOPDT parameters from the Bodie plot.